In this video, we're going to look at some examples of how to determine whether or not a molecule is polar or nonpolar. So in general, this is a two-step process. We first have to determine whether the bonds are polar. If all the bonds are nonpolar, then the molecule has to be nonpolar. The molecule can only be polar if it has polar bonds. However, even if the bonds are polar, if the dipoles cancel each other out, then the molecule is still going to be nonpolar. Right? There's going to be no net distribution of charge because the dipoles cancel each other out. So the molecule can only be polar if it A has polar bonds and B if the dipoles or the polar bonds don't cancel each other out. So just a reminder, if I need to know whether or not the bonds are polar or nonpolar, I need to remember the cutoff. So if the difference in electronegativity between the two bonded atoms is between 0 and 0.4, then that's a nonpolar bond. So the bonds are only polar if the electronegativity difference is greater than 0.4. All right, here's our chart of electronegativities to remind you what those look like. All right, so just a couple quick examples, and then we'll get into doing some ourselves. So molecules like H2, Cl2, and CH4 are all nonpolar because they only contain nonpolar bonds. Right? I think this is obvious for H2 and Cl2, right? Hydrogen is obviously the same as hydrogen, so the electronegativity difference is 0. So these two are both going to be nonpolar molecules. In the case of CH4, I have different atoms, but if I look back at my electronegativities, the electronegativity difference between carbon and hydrogen is just 0.4, and so the carbon-hydrogen bond is nonpolar, so the molecule overall will be nonpolar. Now, in molecules like carbon dioxide, where the oxygen-carbon bond is polar, because those oxygen atoms are arranged symmetrically around the central carbon, they're actually going to cancel out, right? If we imagine a tug of war for the electrons, because these oxygens are pulling opposite one another, there's going to be no net movement of electrons, and the molecule is going to be nonpolar. Now, here's a couple examples of molecules that are polar. So, in the case of HCl, the hydrogen-chlorine bond is polar, right? And the chlorine is pulling on the electrons to the right. There's nothing over here to cancel it out, and so we're going to end up with the electrons spending more time around the chlorine than they are around the hydrogen. So the chlorine is going to be partially negative because it gets more electrons. The hydrogen is going to be partially positive because it's lost the electrons somewhat. And so we would say that HCl is polar because it's got a negative end and a positive end. Same thing happens with water. So because the shape of water is bent and the oxygen and hydrogen bonds are polar, right? The oxygen is net going to be pulling the electrons up, right? Because both the hydrogens are down. There's nothing to counteract the electronegativity of the oxygen. So oxygen ends up being partially negative. The hydrogen ends up being partially positive. So because we have this separation of charges, we would say that water is a polar molecule. All right, so here's our first example. So in order to do these, we need to be able to draw the Lewis structure and determine the molecular shape. In the interest of time, I'm not going to guide you through all those steps, but if you want to know how to do that, please look back at my other videos on drawing Lewis structures and then the separate video on determining the molecular shapes. So here's the Lewis structure. So HCN has 2 electron groups, so it's linear. So now we want to know, does it have polar bonds? So from our previous discussion, we know the hydrogen-carbon bond is not polar. If we look at the electronegativity differences between carbon and nitrogen is 0.5, so the carbon-nitrogen bond is polar. So we do have polar bonds. Hydrogen is not pulling as hard on the electrons as nitrogen, right? So nitrogen is going to be pulling on the electrons. The hydrogen can't cancel it out, so the dipoles do not cancel. And so if I have polar bonds and the dipoles do not cancel, then the molecule is going to be polar. Here's carbon tetrachloride. So I've already given you the Lewis structure. The electron geometry and shape are both tetrahedral. So let's look and see if the bonds are polar. Carbon at 2.5, chlorine at 3.0. So we do have polar bonds. But now when we consider, do the dipoles cancel? Because I have carbon atoms in each one of the positions, these dipoles are going to cancel. Uh, and so the dipoles do cancel, and so the molecule is going to be nonpolar. But I think for linear and trigonal planar molecules, it's a little bit more obvious that the dipoles cancel. But in general, as long as there are no lone pairs and all of the atoms connected to the central atom are the same, those dipoles are always going to cancel out, and so those molecules are going to be nonpolar. All right, here we have NF3. Here's the Lewis structure. The shape is trigonal pyramidal. Now, if we look to see whether we have polar bonds, so nitrogen fluorine bond, different electronegativity difference of 1.0. So I do have polar bonds. And then we look to see whether the dipoles cancel out. Now, because I've got this lone pair sitting up here, right, we've lost the ability of the thing up here to cancel out the net downward pull of the electrons. And so we're going to end up with a negative end of the molecule on the fluorine side. The nitrogen end is going to be partially positive. So the dipoles do not cancel out, and the molecule is going to be polar. All right, last example. I have C3H8. Now, in this case, I only have carbons and hydrogens. If you remember from our previous discussions, the carbon-hydrogen bond with an electronegativity difference of 0.4, all of those bonds are going to be nonpolar because I can only have bonds between hydrogen and hydrogen, or carbon and carbon, or carbon and hydrogen. So none of those bonds are going to be polar. So if I don't have any polar bonds, it doesn't even matter what the shape is, the molecule is going to be nonpolar.